introduce a parameter alpha. There's something I want to do. When alpha equal to 1, plug in 1. When alpha equal to 1, that is going to take you back to the exponential. So the alpha is the numbers of events more than 1. When alpha equal to 1, you are into exponential. I told you time, gamma is a generalization of the exponential distribution. You know what? The alpha, the gamma have to be non-negative. Of course, you don't expect the numbers of events to be negative. Alpha is the numbers of events. So alpha has to be greater than 0. And beta has to be greater than 0. And of course, there's a lot of flexibility here. What I'm trying to display now is when I vary the values of alpha and beta, I'm actually going to have different shapes. Having different shapes, that means flexibility. But you know what funny thing? When alpha equal to, and that was why I said the special gamma distribution for which alpha equal to 1 is basically exponential. Just wanted to take note of that. So the other one where alpha equal to 1, okay, that is basically an exponential distribution. Okay, so this is the shape. Now, of course, using the idea of gamma function, you can actually evaluate example 6.26. You know, whether in exponential or in gamma distribution, you can make use of a gamma function. Does that make sense? Now, let me now tell you this. If I have a gamma distribution, the mean and the variance, the mean is alpha beta. Something is very interesting here. If you plug in alpha to be 1, what is going to happen? They're going to become the mean and the variance of the exponential. Take a look at that. So the same way I derive the mean and variance of exponential distribution the other time, you can also attempt that of the gamma. Okay, to arrive at what we're seeing right now. Okay, let's take a look at an example. A biomedical study determined that the survival time in weeks. You know, we use exponential and gamma distribution in survival analysis a lot. And not only survival analysis, in reliability study, in engineering. Okay, whenever you're trying to figure out the time you're going to wait. In fact, insurance claim just follow gamma distribution. How long is the insurance company going to wait until they will be called to action? I know they don't want to be called to action, right? They want to be getting money, and they are hoping that everything is going to be fine, right? Okay, so how long they need to have a statistician or a modeler that will tell them on average, the time they're going to wait, before a particular, customer will put on a claim. Okay, let's take a look at this. A biomedical study determined that the survival time in weeks has a gamma distribution with alpha equal to 3, beta equal to 4. Okay, for a certain dose of a toxicant, what is the probability that a rat survive no longer than 10 weeks? The fact that you've been told about the probability distribution, and not only that, you've also been given the values of the parameters, you should be fine. All what you're just going to do here, okay, is to make use of the distribution. I'm actually going to write that for you. You can try that. Okay, you can actually try that. Okay, when S follow gamma, with parameter alpha beta, okay, the f of x equal x raised to power this, exponential raised to power this, gamma alpha, beta raised to power alpha. This is the distribution. X greater than that, this greater than 0. And right now, what you want to find is you've already been given alpha to be 3, beta to be 4. That you're going to plug in here. Okay, when you plug that in, that becomes a function of x, right? And what do you want to find? The probability that rat survive no longer than 10, no longer. Oh my God, no longer than 10. You're actually going from 0 to 10. Oh, you understand what I mean? You want to integrate this guy, f of x, dx. That is what you want to do. Okay, then you're going to make use of the resulting function after plugging in the values of the alpha and beta. Does that make sense? Okay, so no longer than 10 is at most 10. You're going to start from 0 and heading 10. Okay, the next one is the chi-square distribution. But let me tell you, I'm not going to spend more time on the chi-square. I'm going to spend more time on the chi-square. There's a relationship between a chi-square and a gamma distribution. You know, the relationship is just like when I have a gamma distribution, okay, given this way, okay, by the time I set alpha to be v over 2 and beta to be equal to 2, I'm no longer in gamma distribution, but now I'm in chi-square distribution. Does that make sense? And you're going to have something like that. That is going to be the resulting expression. Okay, chi-square distribution is a very useful distribution in statistics. You know, it's going to serve as a kind of a territorial jurisdiction to test, you know, whether there's an association between two categorical variables. Like you want to test whether there's a relationship between two categorical variables, whether does the level of educational attainment, does it determine the level of income, stuff like that. We carry out a chi-square test, and of course, if you want to figure out the p-value, we're going to make it of a chi-square distribution. Or what I'm just trying to tell you now, the chi-square distribution actually originated from a gamma distribution when you set alpha to be v over 2 and beta equal to 2. Does that make sense? That's what I mean. Okay, now, of course, the mean of the chi-square is going to be v, and the variance is going to be 2v. In fact, when you go back to the mean of the gamma is alpha beta, by the time you plug in, you know, the mean of the gamma is alpha times beta, right? If you plug in this, what is this times this? V over 2 times 2, that would be v. You see v, right? Then the variance is alpha beta squared. Okay. I think I basically want to move to the last distribution.